Once again, my name is Max Fomitchev-Zamilov. I'm the founder of Maximus Energy Corporation. And today I'm going to talk about my fusion work, but the official title is the observation of neutron emission during acoustic cavitation. Because, and you'll learn about this in just a moment, I don't really know if I accomplished fusion, but I have observed neutrons, and usually neutrons mean fusion, but not always. And I will, discuss those points in just a moment. For the past 3 years, I've been working on bubble fusion, and some of you may know that bubble fusion means a version of inertial confinement fusion. And you know that broadly thermonuclear fusion falls into two categories. We have inertial confinement and magnetic confinement. So in magnetic confinement, we have large setups that involve tokamak type reactors where magnetic field holds plasma together. And in inertial confinement, you are talking about using pressure to keep plasma from spreading and flowing apart. And normally when we talk about inertial confinement fusion, we think of national ignition facility. So in a national ignition facility, we have hundreds of lasers that focus their light on a solid deuterium tritium ice pellet. So it's a cryogenic pellet about a couple of millimeters in diameter. So these laser beams illuminate that pellet, and the outer layer of the pellet evaporates at supersonic speed and launching a shock wave. In fact, a series of shock waves that converge at the center of the pellet, and if everything is done right, then a meaningful amount of thermonuclear fusion occurs in that pellet. And I think recently they reported that they observed for the first time ever fusion yield in excess of the energy that came into the pellet. It doesn't mean that this whole system was energy producing. They're saying it's just whatever energy went into this pellet, which is maybe 1% of the energy that is required to run the lasers, in that pellet produced maybe like 20 or 30% more energy. I don't remember the exact figure. But it's far from being energy producing, and it's a very expensive installation with a bunch of lasers, so hundreds of PhDs and hundreds of billions of dollars are necessary. So I prefer something simpler, and bubble fusion seems simpler. And here the idea is that bubbles are naturally spherical. So when they expand and collapse, they naturally maintain their spherical shape. And therefore, if you get your bubble right, and if you get your acoustic pressure right, basically your sound pressure right, so you can perchance make this bubble collapse so violently to where inside plasma heats up to thermonuclear temperatures. So if you fill bubble with deuterium, perchance you will get deuterium fusion. So this idea is not new. It's been tried by Telyarkin before, and he reported famously in Science. But unfortunately, a scandal ensued, and his work was therefore, I wouldn't say debunked. It was just scandalized enough to where nobody would touch it. It was a 10-foot pole. But because my background is in ultrasonics, I figured this is something that I understand better than anything else, and maybe I can get it to work. So this is what I set to work on in earnest about 3 years ago. And very quickly I realized that bubble fusion only superficially appears easier or simpler than inertial confinement fusion, because at the end of the day, bubble fusion also suffers from instabilities. So it's difficult to make bubble expand and collapse spherically. Rather, I can put it this way. It's easy to make bubble expand and collapse spherically as long as your driving pressures are very mild. But as soon as you are starting to compress the bubble harder and harder and your pressure goes up, bubble develops instability. So the same problem occurs as in inertial confinement fusion. Whenever you concentrate energy, instability always develops and bubble deforms. And here is a good illustration of how the deformation occurs. Basically, bubble develops a jet, and that cavitation jet impacts on whatever surface. Maybe it impacts on the surface of the vessel where this bubble is floating, or maybe on another bubble. So bottom line is, it's difficult to maintain for a bubble spherical shape when you need to achieve this colossal 1 to 1,000 expansion ratio. So it's sort of back to the same problem. But nonetheless, I decided I'm going to try and do it anyhow. And what you're looking here is a picture of my reactor. So that's the reactor that you can sort of see on my background. So I'm still operating the version of this reactor. But this is the reactor I've built for this bubble fusion work. And I'll show you another picture that's easier to comprehend. It's less cluttered. So in the center, you see my main reactor vessel, which is a 6-inch stainless T. So it's a vacuum T that's filled with mineral oil. Because I'm working with bubbles, I'm working with the fluid. So my fluid is mineral oil. It's multitherm IG4, basically vacuum oil. And inside that oil, I create microscopic or nanoscopic deuterium bubbles. So these bubbles are injected through the circulation loop that has a Venturi nozzle that's hooked up to a deuterium lecture bottle. And this is a circulation pump that feeds it. And behind this, you cannot see it really, it's because it's under the table. It's an ultrasonic driver that sends acoustic waves inside my reactor chamber. And here is my vacuum pump, and in the back is my laser diffraction system that I use to measure the bubble size distribution. But let me walk you again through this. So here is a schematic diagram. So my reactor is about halfway filled with oil. There is an ultrasonic driver at the bottom. It's connected to Branson Sonifier 550 power supply. So all of the components are off-the-shelf components pretty much. So this is my circulation loop that occasionally goes through a Venturi that formulates bubbles. Sometimes I use oil filter to remove particulates. Sometimes I use a secondary cavitation chamber, but it's not terribly important. What is important is to monitor sound. I have a PCB piezoelectric transducer that's connected to the scope to read the form and intensity of the acoustic waves. And of course, to detect my neutrons, I use helium-3 tubes. Neutron counters. So here's a close-up picture at my reactor. You can see that oil here looks cloudy. It looks cloudy because there are a bunch of tiny, microscopic deuterium bubbles in it. And out here, oil is of different color because this oil is not just oil; it's a suspension, it's rather emulsion of heavy water droplets in oil. And you can see that the reactor glass cracked. It's one of the things I've learned and managed to produce is super strong acoustic waves that originate from expanding and collapsing water droplets suspended in oil. And those acoustic waves were so strong on more than one occasion they broke up this viewport glass. But more on it in just a moment. So I will start first with whenever you conduct a nuclear experiment, you're always looking for a marker. And I would argue that at this stage, it's too early to talk about any kind of excess heat in any kind of nuclear experiments. So be that National Ignition Facility or ITER or something else, nobody's measuring heat. Everybody's measuring some nuclear radiation, be that gammas or neutrons. And if you talk in fusion, everybody measures neutrons because if you count your neutrons, you can tell how much of fusion took place, and therefore you can extrapolate how much energy was produced. So nobody measures excess heat. Everybody measures neutrons, and whoever measures excess heat, I remain extremely skeptical of that. So tool of the trade is neutron, and here you see is helium-3 proportional counters that are combined in a bank of 6. So more counters, higher neutron count, higher sensitivity. That's why I use this. I used this neutron bank. And what you see here is the thermal neutron spectrum. So I'm counting thermal neutrons. So neutrons pass through oil and they thermalize. And once they're detected by helium-3 field proportional counter, you're supposed to see this rather characteristic thermal neutron spectrum. So this is how I know that I'm counting neutrons and I'm not counting noise or gammas or something else. Whenever you count neutrons, you should get thermal neutron spectrum. And this is what I demonstrate here. And to succeed at neutron counting, I realized there are no tools on the market that allow doing this easily and conveniently, so I had to develop my own hardware and software. So as one of the outcomes of this effort, I developed this automated nuclear lab system, which you see pictured here, which is a tool for rapid nuclear experimentation. So this system is coupled with software, and it allows capturing data from individual radiation detectors, be that neutron counters or gamma counters or combination of neutron and gamma, or you can connect any nuclear detector to it, and you can acquire data on each channel individually, and you can process this data using the pulse counter pro software, that I also developed to support the system. So this combination of automated nuclear lab and pulse counter pro is an essential tool for me, and I'm proud to say that many other researchers, including a group at MIT, is using it now for their own research, because it's very convenient to capture data, to analyze it, to see spectrum, to eliminate noise, to do all sorts of number crunching and statistical analysis that you must do when you perform a nuclear experiment. So it's a scientific grade hardware and software system that makes this experimentation possible. And key motivation for me was somewhat amateurish approach by a lot of experimentalists to nuclear science, because few realize that taking a single measurement means nothing. And it's the basic principle of nuclear science obeys the laws of quantum mechanics, and in quantum mechanics everything is a random process. So any measurement you take, be that a neutron count, gamma count, X-ray count, any kind of measurement you make gives you a random number. That's just the nature of the thing. So you take one measurement, it means nothing because it's just a random number. So suppose I used my neutron detector, I took a measurement, and it tell me the counting rate is 17 counts per minute. Well, I cannot make any conclusion from it unless I take a background measurement. So I take a background measurement, and it's 13 counts per minute. Well, still, I cannot say that my experiment is greater than my background, because both numbers are random, and in order to compare them, I need to acquire a bunch of samples that corresponds to my background and a bunch of samples that corresponds to my measurement, to my experiment. So here, the background samples are depicted in red, and experimental samples are depicted in blue. And because these are random processes, the more samples you capture, the better this histogram will fit the Poisson distribution. And that's one of those things we look for in nuclear science, because all of these processes are normally distributed. Whenever you quantize them, you get a Poisson distribution. And once you acquired enough samples, you have two Poisson distributions, and you see the overlap quite closely. So the difference between them is not as large as two random samples might lead you to believe. And when you run a statistical analysis, for example, you're doing a student's t-test, and that student t-test tells you what is the probability that both samples, red and blue, are coming from the same distribution. And in this case, probability of that is 74.8%, which means that two distributions, they only appear different, but in fact, they're more likely to be one and the same. So therefore, this is not a statistically significant result. And a lot of researchers overlook the importance of statistical analysis, and therefore they report their data and mislead us in believing that something's happening. But luckily, all of this is done automatically in the Pulse Counter Pro software, and this is what enables me to run a bunch of experiments and have an instant conclusion of whether or not I have excess of neutrons, excess of gamma quantities, excess of anything. And this is how a typical experiment run would be. So out here, red is the background and blue is the experiment. So I'm running my reactor, and my neutron counter is counting, and my software is logging, and I'm getting these red bars, which is my background. Then I turn on my reactor, I start getting blue bars. And the plot here is the p-value plot. So the rule here is the longer your reactor operates, assuming your reactor produces excess neutrons, which looks like it does here, right? But the longer it does so, the lower your p-value becomes. So your p-value must approach 0, assuming that your background is different from your experiment. And the longer you do it, the closer the value will get to 0. So that's why I plot this p-trend. So in this case, this particular experiment indicates, in fact, and it says here, p-value is less than 1/10 of 1,000. So it's 0.000, because I run a bunch of experiments. And every time I turn on the reactor, the flux is slightly greater than the background. But the more times I do it, the greater the statistical significance of this result. And this is how I can show that that the flux of neutrons from the reactor is about, I think, 20% or 30% greater than the background. This is how statistical analysis is done for publication quality results. So with this in mind, this picture tells you how the acoustic signal looks in my reactor. So when I turn on that acoustic driver that's mounted at the bottom flange, I start getting this 20 kilohertz sine wave. And that sine wave is not particularly strong. Amplitude here is in millivolts, but if you convert it to PSI, maybe you get 200, 300 PSI. So it's good pressure, but it's nothing spectacular. What is more interesting is these spikes. So these spikes correspond to pressures on the order of thousands of PSI, or sometimes on the order of tens of thousands of PSI. Sometimes they're so great that they destroy my ultrasonic transducer that I use to listen to these sound waves, and sometimes they break the glass in my reactor. So why do these waves happen? Well, this is something that I discovered that if I introduce water droplets, specifically heavy water droplets, into my reactor, those droplets convert into water vapor bubbles, and those bubbles somehow synchronize their expansion and collapse in action. And I hypothesize that these spikes are caused by constructive interference of shock waves that these expanding and collapsing bubbles launch. Specifically, I think that the shock waves constructively interfere when the bubble rebounds, because that's when it launches the outwardly expanding shock wave. And I think this is an important component for my bubble fusion process. So how do I know that I get fusion going or not? So one day, almost like 3 years ago now, I turn on my reactor, and all of a sudden I'm getting neutron flux in the excess of 1,500 counts per minute, 6,500 counts per minute. So on this plot below, background is so small, I cannot even see it. So background was on the order of 30 counts per minute. And here I have 500, 1,500. So, there were so many counts, I thought, well, maybe I got a problem. So let me look at the neutron detector signal. So I look at the raw neutron detector signal that I captured. And it's replete with the spikes. And each spike here is a neutron signal. So if I expand this plot, so I expand, the horizontal scale, I do in fact see individual, neutron spikes, which appear as vertical lines here. And I see something else here. This, bunched up, undulations that you see regularly spaced correspond to noise that crept into my data acquisition system through capacitive coupling of my acoustic driver to my my data acquisition system. So on one hand, this is noise. You don't want this noise. On the other hand, this noise is very fortuitous because it shows to me that I get my neutrons, which are these vertical spikes, that mostly, by far and large, coincide with the time when my acoustic driver is on. So I see I get the spikes when there is a bunch of undulations here from the basically from the energized acoustic driver. And when the driver is off, I don't see any neutrons. So this tells me that neutrons happen when acoustic waves bombard my oil. So this bolsters the idea that bubble fusion takes place. So when I turn on the sound, bubbles expand and collapse. When they collapse, they generate neutrons, and this is what I'm seeing here. So here's another example of an experiment run over 24 hours. So for about 20 hours, I was collecting background, and you see my background here is in blue. And my background is rather small. Here it's in counts per second, so it's less than 1 neutron per minute. When I turn on the reactor, I start getting these red bars, and you see they're in excess of background massively. So I turn off the reactor, it returns to background. I turn on the reactor, and counts go on and keep growing massively. And in fact, if the reactor is operating, you would expect your counts, or your neutron counts, to increase with time because tritium is produced. So you start with deuterium, and deuterium fusion results in helium-3 and tritium in equal proportion. But deuterium-tritium reaction is much more likely. So assuming that bubble persists through this expansion and collapse process, next time it expanded and collapsed, it has some tritium in it, and tritium is much more likely to react with deuterium. So therefore, one would expect more counts, and this is what I seem to see. And here is, by the way, a zoom on one of this, neutron events, which is actually a multiple neutron event. So each peak here corresponds to an individual neutron. So, this particular bubble, this particular occurrence, resulted in 1, 2, 3, 4 closely spaced neutron events that, I cannot even resolve, with my software, too well. So they are counted as one. And it tells me that, the actual count rate, was a lot higher because a bunch of these neutrons were, synchronous in time, and therefore, cannot be resolved unless, you deploy more detectors. But in order for me to establish, to produce a publication quality result, I had to show that at the end of the day, my neutron spectrum builds into a thermal neutron spectrum. So it took me about 6 months to eliminate all sources of noise and address all potential sources of systematic errors, and to make my reactor work for several hours nonstop, to where I could capture thermal neutron spectrum. And this is, what I've done, and this is what you see here. And at this stage, I was satisfied that I knew that, what I'm counting is not noise, not electromagnetic interference. What I'm counting is neutrons, because the spectrum looks perfectly thermal, and the reactor was operational for over than 1 hour, and the count rate was 100 times in excess of background. So statistics was solid, neutron spectrum looked good, systematic errors were taken care of, and that's what I was able to put in a paper and submit for publication in Nature Scientific Reports, and the paper was published in May, and that was the result that I was able to publish. There was another result that I did not publish because it did not fit my own understanding of the process, and this is the result you see on this page. So once again, red bars are neutrons from the reactor, and blue bars are background. So I start, the signal is neutron counts are at the background, so I start counting as the reactor is turned on, and counts grow predictably. When I turn off the reactor, the counts seem to return to baseline. I turn the reactor on again, counts go, and this time even higher. And when I turn off the reactor, I don't see counts returning to baseline instantly. Instead, they take about 30 or 40 minutes to relax. And that is strange, because the idea is, if this is bubble fusion, if you turn off your reactor, there should be no neutrons, because there is no sound. There is nothing that expands or collapses the bubble. So how come I'm still getting neutrons way above background? So I turn the reactor again, the counts keep going up. I turn it off again, and counts take their time to return to baseline. So as you see, this was happening all the time, and it took it eventually a very long time, like several hours, to return to baseline, completely. So I waited overnight. I started in the morning, counts went up again, and the whole thing repeated. Because this result was so wild, I decided not to include it in my Nature publication, because this smells too much of cold fusion, and I wasn't sure if my paper would be accepted anyhow. So I decided not to make my task even simpler. So if you read my paper, you see that I don't claim fusion. All I claim is observation of neutrons, because according to academic standards, I have not satisfied the requirement of proving that these neutrons are from fusion. And in order to prove it, I would need to detect tritium, and this was a whole other set of measurements that I didn't have a chance to do. So therefore, I couldn't make this claim, and I decided to focus just on reporting the neutron signal. So this doesn't fit the standard paradigm. So I figured I'll sit on it, try to understand it better, and you are among the first people to hear about it. But let's kind of go back to what I know and what I don't know, because what makes scientific work interesting and frustrating at the same time is because there are always more questions than there are answers. And you think you start with one hypothesis, but it takes you somewhere else. And what you think about the process ends up being wrong. And this is kind of the lesson I learned. So I started with trying to prove to myself that I can do conventional thermonuclear fusion within the cores of collapsing bubbles. But this graph shows me that this is not what is happening, because this graph is incompatible with that idea. Yet I see this neutron flux. So what do I know? Well, I know that I mixed my perfect working fluid by accident, because 3 years since I've reported this neutron signal, I was trying, to mix the same working fluid on purpose, and so far I failed. And this is, where the frustrating part of science and discovery comes. So sometimes you're graced with this unexpected discovery, and you have no idea how you came about it, and then it takes years to understand and comprehend it and make do it on purpose. But nevertheless, here's what I've learned. So my main component of my working fluid is mineral oil. And that mineral oil was heavily oxidized from various fruitless experiments. So I would run my reactor for hours, and the oil would get heavily oxidized. So it was yellow and green in color. So it was somewhat green in color because the gaskets in my vacuum system are copper, and oil was in contact with it. So quite possible that I've developed some copper soap that gave oil its green color. And because you see boxes of borax stacked behind me, those were for neutron protection. They were leaking, and maybe some of that borax have gone into oil. I definitely had some deuterium oxide or heavy water in my water because I added it on purpose. And I did have some titanium deuteride solid particles in it by accident. So one of my fruitless experiments was with heavy water and titanium deuteride, and I ended up dumping it into my waste bucket. And from that waste bucket, I drew oil for one of my experiments, and that's when I've gotten my best results. So too bad I didn't record what I was dumping in my waste bucket, but customary, we don't maintain a log of our waste, so I did not. But this is the irony or serendipity of it. I never thought that oil from the waste bucket would do anything, but turns out it did, and now I'm suffering for the lack of a record of what went into that waste bucket. But anyhow, what else was there? Well, there were some deuterium bubbles in it, possibly a small or definitely smaller amount of hexadecane D40, which is fully deuterated mineral oil. Some amount of xenon. What I also know is that my particles, be that bubbles or droplets, carried significant electrostatic charge, because as I was pumping my oil through the circulation loop, the oil was getting charged because when you use a filter has some paper in it. When oil passes through paper, we have dielectric flow goes through dielectric. When you rub two dielectric together, static charge builds up. And that static charge build up, I could see it, I could feel it, and it was my hands. If I move my hand towards the oil, the hairs on my hand would stand. And if I took my electrostatic meter to it, the meter would go to the chart. So oil was supremely charged sometimes, and I could also see the level of the oil from my viewport. It was not flat; it was curved as a crescent of the moon because there was so much charge in it. And I also had this secondary circulation pump connected to the reactor through Teflon tubing, and Teflon is a dielectric, and it was creating another source of charge for that oil. And when you have electrostatic charge, that makes suspended particles, droplets, bubbles more stable against coalescence, against dissolution, and also changes the bubble dynamics perceptibly. So perhaps that was important also. What I also learned is I was able to produce my neutrons when my emulsion was at various concentrations. So it could have been so thick to where it looked yellow because there were so many droplets in it, and it would still produce neutrons. Or sometimes it looked almost clear, and the only way I could see particles in it is when I would shine a laser beam. And then when you have suspended particles, the droplets in your oil, the laser beam would illuminate them, and you would see the beam going through the oil. But if the oil is completely free of particles, it would be clear and beam would be invisible. So I know I was able to do it at various concentrations, and I was able to do it at various pressures also, from a low-grade vacuum of a few torr to down to atmospheric pressure. But most of my experiments I conducted on the partial vacuum of about 4 to 20 torr, and oil was mostly clear, so it had very few particles, because in this particular mode, it was easy for me to get repeatable results. And as I said, I ran my reactor for about 6 months. Day after day, collecting this data and studying, making experiments. So this process was very repeatable, and oil was very stable. And the most often, I would evacuate my oil to about 4 torr, introduce just 1 milliliter from the waste bucket of that magic mixture that I was researching, and I would capture a strong neutron signal until the pressure in the reactor would build up to 20 torr, and then the process would stop. So I thought this was the case because at about 20 torr, water vapor would condense back into a liquid at atmospheric at the room temperature. So that's pretty close to the heavy water vapor pressure at atmospheric temperature. I mean, at the room temperature. So this is what I know. So the results were repeatable and sustainable for months and hours, but unfortunately, after about 6 months, my emulsion separated, and it no longer looked the same. So it looked cloudy, but one day in March, I look at my emulsion and it looks transparent with some sediment on the bottom, and that's when it quit working, and that's when I started my work in earnest trying to recreate this emulsion. Oh, and I also, always used a 20 kilohertz driver when I was getting, successful results, and the driver was with a duty cycle of 200ths of a second. So the sound was on for 200ths of a second, and then it was off for 200ths of a second, and so on and so forth. So what I don't know. So I don't know, as I said, that the neutrons came from fusion. And I mentioned that in order to establish with scientific accuracy that the neutrons come from fusion, you either must capture neutron spectrum, and not thermal neutron spectrum, but actual neutron spectrum, meaning the neutrons must not thermalize and must hit your detector right there and then, so you could capture their true energy. And then if you observe neutrons at energies consistent with DD reaction, then you can say, yes, these neutrons are consistent with DD fusion, therefore, it's DD fusion. Well, if this is not possible, and then it's definitely difficult in my case, because when neutrons originate from oil, they are going to come through oil and they're going to thermalize in the process, and as such lose their original energy, thus producing a thermal neutron spectrum, which is a nice spectrum to have, but it doesn't tell you what was the original energy of neutrons. So therefore, you cannot use spectrum of neutrons to determine whether it was DD fusion or some other type of fusion. So in this case, you must look for tritium. And if you determine that your reactor is producing tritium, it's significantly above background levels. And once again, you can say, yes, my neutrons are from DD fusion because I do get tritium, and the amount of tritium is consistent with the amount of neutrons that I'm counting. And that was my intent, but I never got around to doing it because it took me 6 months to prove that I am counting neutrons and to build this beautiful thermal neutron spectrum that you saw. And I meant to start measuring tritium levels, but that was the time when my reactor quit working and I never got around to doing it. And this is just emphasizes the difficulty of doing, scientific work, especially nuclear work. Every measurement is a difficult one, and every measurement, takes time and expertise and knowledge to do. And measuring tritium is not easy. Perhaps it would have taken me another, 3 or 4 times just to learn how to measure tritium levels. But as I said, I've never gotten around to do it. Yeah, but I will, as soon as I'm able to recreate this magic, mixture one more time. So I do not know whether this was fusion, but it could have been spallation. So if you ask what other process could produce neutrons, could be spallation. So spallation is a very well-known nuclear process when you rip off neutrons from other elements, such as carbon, oxygen, or even metals. So for example, when an ion beam hits a metal, maybe when a proton beam hits mercury, it would rip off neutrons in massive quantities, and that's a very well-known source of spallation. But it's also possible to have gamma quantums rip off neutrons from oxygen or nitrogen and produce neutrons in that way. It's also spallation. So I also don't know whether my reaction took place in the surface or in the bulk. So on one hand, my entire reactor is filled with these bubbles. On the other hand, bubbles collapse both on the surface and in the bulk. So I don't know which bubbles did the work. Perhaps both, or perhaps one kind. But it's a question that needs an answer. So I don't know the exact composition of my working fluid. I listed all the components in it, but I don't know the exact proportions. I never gotten around to measuring it, because I was so focused on darn neutrons. I also don't know the bubble size distribution. So the tool I used that raised the red laser diffraction system in the background, it wasn't particularly good for measuring, the kind of bubbles I had. But that's, again, it's a problem in its own right. How do you measure these bubbles and droplets, and you know that your measurements are correct? There are a bunch of tools you can find for measuring oil droplets in water, but when the problem is in reverse, when you have water droplets in oil, those tools occasionally yield weird, incorrect results. So it's a problem in its own right. So someone needs to spend time on how to measure water droplet size distribution in oil, and once again, I wasn't able to devote enough time to it to obtain certifiable measurements. So I don't know why my neutron signal was increasing with time, but I have an idea. If it was fusion, it would breed tritium, and therefore probability of subsequent fusion reaction increases, because now we're talking about deuterium and tritium reacting. So this is not an exactly accurate statement. I could say I do not know for sure why my neutron signal was increasing with time, but I have a pretty good idea, and it's consistent with fusion. But for the life of me, I don't know why the neutron signal remained when I turned off my acoustic driver. So that's the biggest mystery, and that didn't happen all the time. It happened enough of the time to where I can rule it out as something weird. Most of the time, the neutron signal disappeared instantly when I turned off the acoustic driver, but enough times it didn't do so instantly. So therefore, something else was happening, and that begs an entirely different question, and that question I'm going to address shortly. But before, I want to kind of summarize what I tried. So I spent 2.5 years trying to replicate this mixture, and without success. So I tried to work with heavy oil, and what I've learned is with heavy water in oil, does not produce neutrons. So clearly something else must be tried. So I thought, well, maybe if it's not heavy water, maybe it's this titanium deuteride powder that I had. So I spent another year on this titanium deuteride powder without much success. So I also tried pure deuterium bubbles and deuterium and xenon. That didn't work. Tried surfactants, didn't work. So tried a bunch of things, listed here: charging oil, developing stupendous acoustic pressures in excess of 50,000 psi to where my reactor was bursting at the seams and the welds were coming apart. None of that, seemed to produce any results. So the conclusion that I arrived, it's not a single one of these things. It's a combination of all of these things. And it makes it more difficult because it's easy to, let's say, take oil and heavy water. So you have two things to work on. You can scan the parametric space. But if you have many of these things, the parameters grow in combinatorial explosion. So it's just too many things to try. So how do I approach it? It's kind of a question. So one thing I've done, I've applied for NSF grant. There is a seed fund grant that I was invited to apply, and I did apply. So it hasn't been, decision hasn't been made yet. I don't know if it hasn't been reviewed. But what I know for sure that for me to make progress, I need to basically I need to outsource some of the tasks. And one task is CFD modeling. Another task is high-speed diagnostics of bubble behavior. Third and rather important task is to make a system that mixes bubbles and droplets of specific size. And that's why I applied for a grant, so I could have some money to spend on this task by hiring people who are able to solve this well-defined problems and produce subsystems that I badly need to make progress in a bit more systematic manner. But that's the nature of science. If it was easy, everybody would do it. And I feel like I've done the easy part. Now it's the hard part, and that hard part unfortunately requires money to buy top talent that is necessary to address some of the issues that I highlighted. But what I'm thinking now, I'm thinking that TID is titanium deuteride was probably crucial, because I cannot think of any other way to explain why my neutron emission did not return to baseline right away when I killed the sound. Because if you hypothesize that fusion happens within the solid state, within this titanium deuteride particles, then it's no longer a conventional thermonuclear fusion. It's some sort of cold fusion that we don't know anything about. So who is to say that that process must stop when you turn off the sound? So that's the only explanation that I can think of right now. And I also think that the static charge might be important, because static electricity on the surface of these TID particles could do something. Also, it could prevent these particles from coalescing. And I think the mechanism, the onset mechanism of fusion, is this cavitational jets from droplets, from water droplets or bubbles that I have floating in the soil alongside of my TID particles. They impinge on solid TID particle surfaces and they initiate the fusion. So I'm thinking that I should go back and try generating these nanobubbles again and add some TID particles to my mixture and see if I can get any headway that way. So the working theory, once again, I think my mixture must contain these three components. So it's, first of all, it's oil, but within that oil I have this D2O droplets, and these D2O droplets turn into D2O water vapor bubbles, and those bubbles expand and collapse violently and create these cavitation jets that impinge on solid titanium deuteride particles, and the fusion happens in solid state. So if that is the case, well, I'm thinking about making a bottom flange of my reactor from titanium and deuterate the surface of it, to maximize the surface area, and then introduce the fluid and see if the cavitation jets impinging on deuterated titanium bottom plate of my reactor would produce massive amounts of fusion. So that's on my to-do list. But I also tried synthesizing my own titanium deuteride powder. So before, I was using titanium deuteride that Alan Smith made for me, and that powder was rather coarse and it was electrochemically loaded. So I said, maybe I can do some of that powder. I thought I have a picture here. Somehow I don't. Well, I thought I would make that powder myself. So I took a cylinder, which you cannot see. It's behind this neutron detector. And that's, the picture here, which is missing. I apologize for that. So this cylinder, which you cannot see, is filled with titanium sponge. And then from the cylinder, deuterium gas is fed into that titanium sponge. And then the cylinder is heated. And when the cylinder is heated, the titanium sponge is heated. It absorbs deuterium. And as I was doing it, I was capturing neutron counts. I thought, what if, I get some anomalous neutron counts just from the deuterium loading into a titanium sponge. So the blue is here is background, and red is, when I actually applied heat and when hydrogen started being absorbed by titanium. But these counts are consistent with background. So you see the red bars are now taller than the blue bars, so the count rate wasn't changed. So the p-value approaches unity, which means natural neutron background is the same as the neutron background when deuterium is absorbed by titanium. It was just a curious experiment to try. But at the end of the day, I developed enough of this powder, about 1 pound, that I put on eBay for other, researchers to try and experiment with. And that's the powder I intend to use in my subsequent set of experiments. Which also, give me some other ideas. What if maybe, surfactant is more important, or maybe, static electricity is more important, which reminded me of another work by a Russian group that happened about 20 years ago in Russia. So what you see here is a reactor very similar to mine, and it's also filled with mineral oil. And that oil is passed through that reactor through a Venturi nozzle. So that's an elongated Venturi nozzle that you see in the middle. And it's passed under very high pressure. And as oil exits the nozzle, it glows. So they don't really know why it glowed. And I think this result in its own right is just unbelievably interesting. So you pass oil through a Venturi nozzle at such a velocity that the oil glows. So I think this glow is electrostatic in nature, because oil is electrostatic and it rubs against the bulk of oil that is static. So the oil jet impinges on the bulk oil, and charge separates, and the charge creates so much friction, and you have a bunch of this electrostatic discharges jumping on and off, and this is the glow you see. So I thought, well, this is very interesting to try to do this setup and introduce my heavy water droplets or my deuterium bubbles in it. But this is a bit of a scary experiment to do by yourself, because oil is under pressure, and if it bursts, it can ruin my lab or even ruin me. So I'm interested in doing this experiment, but I'm wary of doing it by myself, because there will be nobody to hold my body away from from the sparkling wires or from the cutting jet of oil that bursts through the line. So I'm kind of being a chicken at this moment, trying it by myself. But maybe if I get funding from the grants or find a collaborator, I could try a version of this experiment, and we could see if we get neutrons this way. So the guys who did this work in Russia 20 years ago, they didn't use deuterium or deuterated oil. They used just ordinary mineral oil, and therefore they didn't detect any neutrons. But I think it's a very interesting work to build on. Well, my talk is coming to an end. So because my publication in Nature Scientific Report created a lot of interest, I was encouraged by a few folks to put my project on WeFunder. And WeFunder is a crowdfunding platform that allows anybody to participate in this project if they find it interesting. And few people did. So to learn more, you go to wefunder.com/maximus.energy, and you learn everything about it and how you can participate. And that's all I can say. It's under regulation crowdfunding. You don't have to be an accredited investor, but if you can raise a little bit of money, this research can go to the next stage, because I'm pretty much at the end of where I can make progress on my own. And clearly, additional involvement of technicians and skilled people are required in order to make progress, because there is enough of there is just too much work for a single person to do. And finally, if you want to read more about what I've done, of course I refer you to my paper, Observation of Neutron Emission during Acoustic Cavitation of Deuterated Titanium Powder, Nature Scientific Reports. It's an open access. You can read it freely online. I also encourage you to visit my paper, Reliable Neutron and Gamma Detection, which is published on my website, maximus.energy. So that paper describes the neutron measurement techniques I reference. If you want to learn more about the hardware that I employ, the hardware that I make, I have a white paper about it called Automated Nuclear Lab, and a paper describing the pulse counter software. So everything I do, I hold nothing back. Everything is disclosed in my publications, how the software works, how pulse processing works, how spectra is reconstructed, how hardware acquires data. So all that, you can read. So, and some of additional results, are published at Maximus Energy blog under Bubble Fusion, which you can also review.